In this video, I'm going to be talking about how to translate graphs with numbers. In this first column, we have one blank position versus time graph, and here is our velocity versus time graph representing the motion, and a blank acceleration versus time graph. We're going to take that middle graph and translate it over to our position versus time graph and acceleration versus time graph with two different strategies. Now, when you want to go up to your position versus time graph, the first thing we need to do is find the area between your line and the x-axis. So for this one, it happens to be a right triangle. So we're going to go ahead and find the area of that triangle. So for the area of my triangle, I just used 1/2 base times height, 1/2 10 times 8, and that gave me 40 meters. So I know a couple things. I know that my object is going in the positive direction because all of my values are above the x-axis. I know that it's increasing in speed, so it is going in the positive direction and going progressively faster. And then it's going to be displaced 40 meters from its original position. Now my velocity versus time graph doesn't tell me the initial position of the object. So I'm just going to go ahead and assume that it's starting right at 0, but it could technically be starting at any spot. The velocity versus time graph just doesn't provide that information. So because it is speeding up in the positive direction, I know it's going to be curving upwards, and it's going to end 40 meters from its original position. Now on our position versus time graph, we want to make a curve that's going in the positive direction, so it's rising on the graph, but it gets progressively steeper to show that the rate at which it's moving is increasing. Now going down to our acceleration versus time graph, we find the slope. Okay, so the rate at which velocity changes per time is the acceleration. So if you want to go ahead and find the exact slope of this line, it basically just rises up 8 and then goes over 10. Technically, it would look like this. And we would have an acceleration of 0.8 meters per second squared. And because we have a constant positive slope, we want to show that we have a constant positive acceleration. Now going to our second graph, we're going to start again from the middle graph. And the technique for moving from the middle graph to the top one is we want to find the area between the line and the x-axis. So for this one, it's going to be two rectangles. We have one rectangle over here and one rectangle below. So I'm just going to find the area of the two rectangles. This one is 7 wide and 6 tall. So this displacement is 42 meters. And this one goes over from 7 to 10. So it's 3 wide and it goes down -2. So it's going to bring us back 6 meters. So then because I have a constant positive velocity, I'm going to show a constant positive slope up to 42 meters in 7 seconds. And then for the second portion, I want to make sure the displacement is -6. So I'm going to bring myself back from 42 back to 36 meters, because if I'm going 6 back from 42, it's going to be 36 as my final position, and that's after 10 seconds. Okay, so the time is going to align to be the same thing no matter what graph it is. And again, when we go from the velocity graph to the position graph, we just want to find that area to find the delta x or the displacement for each of those sections. Now going from here to here, again, we still find the slope. And for this one, it's easy, although it might seem like there's two different accelerations. We're just looking at the slope, the rate of change of the velocity per time, and there is no change for this part or this part. They both have a slope of 0. So we're going to put a line right on the x-axis, which would show that the acceleration is 0 meters per second squared, meaning that there is no change in velocity for those particular time frames. All right, now going into our last one, we are now going from a position versus time graph to a velocity to the acceleration. And for the very last one, we are going to find the slope of the position versus time graphs for the position versus time graph and the two segments in order to find our two velocities. Now, if I'm taking a look at it for the first section over here, there is no slope. The slope is 0. So I already know that up to the first 5 seconds, my velocity is going to be right on 0. For the second part, I do actually have to solve for a slope. It ends at a position of 0, and it started at a position of 4 over here, and then ended at a position of 10, or excuse me, a time of 10, and it started at a time of 5. So that is negative 4 over 5 or negative 0.8 meters per second. So I could put a flat line here up to 10, and I'll say that is negative 0.8. Okay, so I have a constant positive slope of 0, so I'm going to be right on 0, and a constant negative slope of negative 0.8 to show a constant negative velocity right over here. And now going from this graph to the bottom one, again, finding the slopes is going to be pretty easy because I have two flat lines, so there is no change in velocity for the first section or the second section. So we have two sections that have an acceleration of 0 meters per second squared again. Now I went from either the velocity graph up to the position versus time graph or down to the acceleration versus time graph, or I started from the position versus time graph and worked my way down. The only combination that I didn't show is the acceleration versus time graph and working my way up. That is a fairly uncommon one because the acceleration versus time graph doesn't tell us much information. But say, for example, you were moving from here to here. Anytime you want to move in the upward direction, as far as going from acceleration to velocity to position, you always find the area underneath the line or between the line and the x-axis. Okay, so if I were to find the area of this one over here, it's 10 seconds wide and 0.8 meters per second squared tall. So 0.8 times 10 tells me the velocity is going to change by 8 meters per second. And then if you take a look at this original graph, you see it changes from 0 to 8. Okay, so again, going from this graph to this one over here, we don't know the initial velocity, but we just know that the change is 8 meters per second. And then going from this one, velocity versus time graph to the position, we know the change is 40 meters, but we do not know the initial position, but we are able to displace it that 40 meters. So I hope that was helpful in helping you translate graphs with number values. Thank you for watching and listening.